All right, I think it's 9:30. We're gonna get started. We got a couple of things to do today. Last time, oh, what did we do? Oh, last time we printed, or I showed you the giant vase, and we had some areas that just didn't kind of have enough flow. They were a little thin on the layers. They look fine-ish, although you can see some ripples in the surface, and looking at it in person, you can actually see gaps where there's not enough filament in there. So we've got some flow rate issues. So we're going to do a little bit of things related to that. First, I've got a couple of little things to show you over here, and then we'll talk about the flow rate and all that kind of goings on. Let me see. Oh, we have two actual viewers, and one voted some material other than PLA, and the other one has not printed anything other than PLA, which is fine. PLA is probably the thing I print the most of. I asked that question though because I've got two other, well, one of these is PLA, the other is not, and we wanted to try and print some of this stuff. So that's going to be a whole issue. So let's look over here at what I have printed. Let's see, that'll be this one. We're a little off the screen there though. There we go. This is PLA. I just finished it, and it's multicolor. So it does have stripes in it. Normally these don't have stripes when you print them like this, but I think it's probably a function of, remember we put that gigantic nozzle on this one. It's a 0.8 millimeter nozzle, so that's probably a function of what's going on here. Oh, when we have some, I don't know, something got hung up right there. It's a little gap. I'm not sure. Maybe it didn't feed right, or it got tangled maybe. But what this is this is one strand of filament, but it has three different colors mixed in with it. Let's see if I can find a little piece of it. It's still loaded in the printer. Let's unload it. We need to unload it anyway. So once it gets heated back up, we'll look at the filament itself. But it's multicolor, and there are dual color. There are this is a tricolor one. I don't know if there's a quad color. Maybe there is. I have not seen one, but this one is blue on one side, a reddish magenta on one side, and a gold on one side. And then where they mix together, you know, there's an orange and a green and a purple over here somewhere, I guess. Yeah. So it's a pretty cool filament if you want to have a little bit of variety. It's also a silk filament. You can kind of see it's very shiny. So I wouldn't use it for strength-related functional parts. Although it's fine to, you know, handle. It would be pretty easy to crack it, but that would be true of any thin wall. This is just a single wall filament. So let's see. Oh, it's still heating up. So that's an interesting thing. They also make transition rolls of filament. I don't have one of those handy. Well, I kind of do. This one, where I don't even know if you can tell. It just goes from a dark green to a light green. So these transition rolls, sometimes they're on purpose, like they're trying to make a rainbow filament or whatever, and they'll just continually change out the color. So the strand will go from green to yellow to blue or whatever colors they put behind one another. Other times, like this one is just the machine they were using. They were making one color filament, and they wanted to stop making that color, and they wanted to start making a new color, and the transition between those two colors kind of mixes them together. And so you can sometimes find transition rolls that are cheaper. Although it looks like nowadays they are selling the transition rolls for like that's the whole point of the roll, is that it's a transition roll, and so there's no cheaper than the regular stuff. But it used to be there were some sites where you could get the transition rolls for quite a bit cheaper, because the color, you know, you're not going to match it to anything. It's going to be this, it's going to go from one to another, and in between it's going to be a mixture. Oh, here's the filament. So you can kind of see, I don't know if you can focus on it very well or not, but oh, well, let's cut the end off because the end's all melted together. Let's see. Now you can have a bed, still blurry, but you can kind of see that it's a three color: gold, red, blue, all in one filament. So they're kind of fun to play with if you're interested in just different colors on your print. This filament is another one. We haven't really talked much about this. I think I mentioned it once, but this is a TPU, so it's a rubbery one. It is not typical PLA. This is a different material entirely. It's called TPU. And you print it, and it is, it's rubbery. So if you need flexibility in a part, again, this is just a single wall print, so it's actually really rubbery because there's hardly any structure to it at all. But if you need some flexibility or a soft surface, a bumper or something like that, then TPU might be the way to go. I did print this on our regular Ender 3. Well, ours has the larger nozzle on it, but other than that, you could print a regular Ender 3 with no changes. It does print a little bit slower, so in your slicer you do have to make sure that you're on a TPU material and not just a regular PLA or whatever. It prints slightly hotter, maybe 220, but the big thing is that it has to go pretty slow. And, now in this model, that's not a problem. There is no retraction. It just creates walls. But TPU can be stringy because it doesn't do well with retraction. Particularly on this kind of printer that we have here with the Ender 3 having this long tube. The retractions, it's kind of hard to deal with compared to a direct drive printer. But it printed completely fine on this Ender 3 in a vase mode setting. And it will print. You just may have some cleanup on oozing and that kind of thing if you have a print that needs retraction settings on. So TPU, maybe we'll do a whole issue on TPU, and it's there are a variety of these. They come in different flexibilities and obviously colors, things like that. But what we're trying to get to is we want to print this stuff. Not for any particular reason. I just want to see if it's printable on a regular Ender 3. I suspect it's not for two reasons. One is that it prints at 240 is the very lowest temperature recommended, and that's at the upper end of what we can do on this Ender 3 without modifying it. So the other reason is this particular roll has just been sitting out, and this is carbon fiber filled polycarbonate. So polycarbonate is Lexan. Lexan is polycarbonate would be a better way to say that. So Lexan, like you might go to Lowe's and they've got the little section of clear plastic materials. They usually have acrylic, a clear acrylic sheet there. And they sometimes will also have a clear Lexan sheet there. So that's this stuff. Now this is clearly not clear. This has carbon fiber chopped up particles in it. They're probably not very long particles. They're probably little fine grains of stuff, but it is in there. A lot of times you'll see carbon fiber put into printable materials, not necessarily to improve the strength, but to keep it from warping. So polycarbonate is one of those materials that has a lot of issues with warping. We're supposed to keep the bed at 100 degrees Celsius. I don't think this bed will even go that hot. But we're supposed to do that, and we're supposed to print it at 240, which is kind of the upper limit for our printer here. But we're going to, and polycarbonate absorbs moisture from the air. This has just been sitting out for a while, so it's probably pretty brittle. We can check. Let's see. Let's check. It's actually not too brittle. It didn't snap. Flexible steel, so that's good. It could be that it's going to be a little bit bad surface finish when it prints, just because the moisture inside of it might be problematic, but it won't stop it from printing entirely. It just may not have a great surface finish. All right, let's load this up and see what happens. So I am going to put it on our little, our little two-part spool here, just to keep from tangling a little bit. it's got a tie on it that I've got to figure out how to get undone. Alright, let's load this. Now I'm going to have to heat it. It's currently at, well, actually it's currently at 35, so we're going to definitely have to heat above that. Let's chop our end off at an angle. Get it loaded. And let's go over to Cura. Do I have, yes, I have Cura running. So let's go over to Cura. And let's see if we can set this up based on what our little card says. Oh, well, first let's just see if there is a polycarbonate material listed in here. I don't know. Generic. There is. There's a generic PC polycarbonate. So we will discard our changes. I'm going to do the layer height to what I've been doing. So that could be a little bit of a problem. I've been doing 0.4 millimeter layer heights, but with this thing, we could have some melting issues. So let's do a 0.2 just to give it a chance. It's going to make the print longer, but that's okay. Let's see, what did it set the bed to? Oh, it put the printing temperature at 270. I really don't know if our printer can go to 270. I'm going to set that down to 240. There is the filament loading. Let's go back over there. Let's see. So I've got the nozzle over here. So it's going to try and purge some at 200. So it might work. I don't know. Stuff is coming out, but it's really the leftovers from the tricolor filament. But the polycarbonate's mixed in there. It did extrude. Okay, we will continue there. So I feel good about that. Let's go back here. Let's go to 240 because the hot end. So remember we had drawn a picture. We had drawn a couple of these pictures. This picture in particular might be useful. So what the problem I'm worried about is this. Inside, well, let's do blue. Inside of here, down into maybe, I don't know where it's going to end. Let's say there. There is the tube, the Bowden tube. So, this tube right here, it goes all the way down into the heat break, down into the heat block. And that heat block is going to be at 240 degrees. We have a heater, you know, right over here. Make it actually a red heater since it's heating. So we've got our heater right here at 240. Well, actually, we don't know what the heater's at, but the thermistor that is measuring the temperature is keeping the area around the thermistor at 240, and thermistor's like right over here on the side. So maybe our thermistor is, you know, right there, somewhere nearby, and that's at 240 degrees Celsius. Which the problem is, this tube is made of Teflon, and it starts to break down around 240 degrees Celsius. So maybe like 250 or, you know, somewhere a little bit higher, but the exposed time at 240 is probably going to be a problem. And I certainly don't want to go to 270. So that's what I'm worried about. But let's put it at 240. They have the build plate at 107, which again is what this our little card recommends, 110 or 100 to 110. I don't think it's ever going to get that hot. I'm going to go to 85, and that's what we're going to do. So print speed, it says 50 to 200, so we're at 50. That's probably okay. That's also, I did lower the layer height just to, let's go to 0.3 so it doesn't take quite as long. I'm worried about the volumetric flow rate. because we've got to melt this material now that melts at a lot higher temperature, but we are printing hotter. So maybe it'll even out. Cooling, it doesn't say one way or the other, but the default settings here set the fan speed to 0, so apparently it doesn't need cooling, according to Cura. And I am also in spiral vase mode. Actually, I'm not. Spiralize outer contour. Now we are, because I want to print just a single wall vase. Okay, I'm going to leave that there. Let's slice this. 58 minutes. All right, we'll preview, and that looks like what we want. Our flow rate. Oh, it's not asking for a lot of flow at all. 6 cubic millimeters per second. So that's not too much. All right, let's save this to our SD card and see if we can get, well, see what happens. I don't know. Okay, we will save to that. Let's call this PC Vase 57. Vase 57 is the name of this model on printables.com, the Prusa site. Let's eject our SD card. Let's go back over to our printer. See if I can get the SD card in there. Having issues with it. Okay. All right, so we have our printer. Let's clean this. We do have our what was it? Layer near bed weld, but I'm going to try with the only mod we've made is the hardened steel nozzle, and it is a 0.8 millimeter, although I'd rather it be a 0.6. So I don't want to use anything other than that. We do need the hardened nozzle with this, since it's carbon fiber filled. It's going to eat up a brass nozzle pretty fast. So let's clean this with just our, this is just our isopropyl alcohol. And let's see what happens when we try to print. Nope, I didn't want to do that. There. All right. So it is doing its homing routine, and gonna try and heat up. So we'll see what happens. We'll leave that alone for a little bit because it's going to take a while to even get heated. And then once it starts printing, we'll check on what might be happening. I don't know. In the meantime, let's go over here and just check out some of the things that we've got going on. We're going to look at the change in the hot end, right? Because we have this hot end currently that is scraping by to print this polycarbonate. And we want to print polycarbonate more easily. And so we're going to have to change some things there. So let's look at what we're going to change. I have got this little guy. So on the screen here is what this is. I got it from Amazon, $35. It's Creality's all metal hot end. And so what that means is that the part that we were talking about before, this little tube, there's still a Bowden tube because we still are using the feeder mechanism connected to the hot end through the tube. So it still is there, but now it ends, it ends somewhere up here now. So it's not in the heat block region. It goes down through the heat sink and down into the heat break a little bit, but it doesn't go down into the heat block. So that's where it's all metal. Even though there's still a tube connected to it, the tube does not enter down into the heat block area. So I don't think they give us a real picture of that, but this is kind of what it is. It also has a bimetallic heat break. You can kind of see here in the middle of the screen where, actually let's get that close to the, there we go. You can kind of see that here where it's got a copper and probably a stainless deal here. So what they're trying to do is they're trying to get mitigate where heat is conducted. So you want heat to get conducted to the heat sink so that it goes away, but you don't want all of the heat going there. And so it looks like they've got a copper and stainless heat break in there. I haven't actually opened mine, so I don't know what it looks like in person. We'll have to look at it in person. Looks like the block is aluminum, probably. That would make sense. Slightly different design on the block. Oh, it's a 3mm thermistor. That should be fine. I think that's what we already have. There are different sizes of thermistors. Also, you'll notice this goes up to 300 degrees Celsius. There are some materials that need to go higher than that even. And then the limit becomes not necessarily these materials. You know, they're okay to 600 degrees Celsius if you have aluminum or whatever. But the problem ends up being that the thermistor does not read accurately much above 300 Celsius. So you have to switch thermistors to a different way to measure the temperature. So there's this, you're chasing these different limits at if you're trying to print hotter and hotter materials. I don't really think we need to go much above 300 Celsius for anything we are going to print, but there are some materials that need even hotter than that. Let's see. This is going to be a direct bolt in to what we already have. So these two holes here are just going to unscrew. We're going to put our new piece in, refit the Bowden tube to it, and put in the heater we already have and the thermistor we already have. And it'll be ready to go. Let's see. There's kind of showing that bimetallic heat break. Oh, here, okay, so the heat break, actually, it's titanium in the core, and then copper on the outer core, or the outer part of the heat break. So the titanium, because look how thin it's going to be. Our printer just started. So titanium's actually not great heat conductor. Plus, we need the strength for this thin wall here to not be too fragile. Looks like they've got a roughness on the inner wall that has been minimized. 0.2mm wall thickness for the thermal insulation, plus that is titanium, which is already not great thermally, or at least not compared to copper. It says that there's polycarbonate is one of the things listed that's going to print. Let's see what's going on over here. So, alright, so here's the issue. It is extruding, but our purge line did not at all stick down, which is, you know, kind of what we assumed. But let's see if it'll stick in our clean spot here. It is not sticking at all. Alright, so let's stop that print and get our little tweezers here to get the nozzle clean, because there's a bunch of, you know, that's what came out and didn't stick anywhere. Let's give it a shot with our bed weld. I assume this stuff is shake the bottle and apply it. Okay. So let's see if this makes any difference with poly. This is not designed for polycarbonate. PLA, ABS, ASA, and PETG. So it's like it's starting to flow out now. Okay, so that's on there. Kind of smoking a little bit. Maybe I was supposed to apply it cold and then heat it up. I don't know. Print. Let's print on that and see if that helps it stick or not. And let me check and see. It doesn't exact. Oh wow! All right, so it does give a warning. Extreme adhesion can occur at high bed temps. So we're at higher bed temps here, so it could be extremely adhesive. We'll find out. All right, back to what we were doing. So this stuff I'm printing, I could not actually find the polycarbonate that this is from. This is from Sliceworks, but when I went to their website, it still exists, but they did not have polycarbonate on there. So they had a bunch of other things, and they were neat looking, but I didn't see a polycarbonate. So I went and found some other polycarbonate. Well, they're showing the Spider all-metal hot-end kit that we'll be applying soon. They do have a 3.0 high temperature, high flow kit. I did not get that one. Let's see. Here I did find, so this is 3D Tech. I don't know if that's how you pronounce their name or not, but that's what it looks like. And 1.75, 750 grams, so not a whole kilogram. And let's see, I think I have to, there we go. $88 for 750 grams of their version of polycarbonate carbon fiber filled filament. I did find some on Amazon. I had actually bought a variation of this at some point in the past. I don't think I used it on Ender 3 though. I used it on a different printer at school. $119. Now this is a 2.5 kilogram. So what is that per kilogram? 119. So that's $48 per kilogram. So it's not cheap as PLA, but probably if you're trying to print polycarbonate and carbon fiber filled polycarbonate, you're looking at something where you're looking at something where you're trying to get some high temperature resistance, even higher than ABS. So maybe you've got this stuff going in a really hotter space, like 110 degree Celsius space. And so you need that heat deflection. It is also very tough material, polycarbonate is. Hey, we're ready to print, or try to print again. Let's see what happens. Oh, a question about my parts fan cooler is the exact same one that came on it. That's not a thing I've changed. So it is, would I call it decent? I mean, it's functional for PLA, but it is nothing special for anything other than it's what came on the printer. So no, I do not have anything unusual there. All right, so here we are on our. Oh, well, there's a like, it's wanting to stick down, but it's just not. You know, there's a little bit of it, but just not sticking down. So why don't we pause the print and let's see if we can get the bed up hotter, because one of the things that and chamber. So the chamber issue, that's our next step here. Is we're going to move this into a heated, well, not a heated chamber, but a chamber where it can not have just be out in the ambient temperature, because that's going to also be able for us to print this a lot better. So we're working our way up from basic Ender 3. Can it at all print polycarbonate? So far, no. So far, we have not had even it adhere. What I'm going to do now is I'm going to raise the bed temperature up to a little bit more. So I'm just doing that on the screen here. Let's go to, see if it'll go to 95. That's closer to what it recommended. So let's go up to there and see if that'll help it stick. And the printer that I would normally print this on, let me show you what I would normally print this on this material. So here's the printer I would normally use for this. Is one of these. I have the well, it's an older version, so do they even still sell? I don't know if they even still sell the one. There's the one I have back from 2020. So the XCF, so it's specifically for carbon fiber and nylon infused carbon fiber and that sort of thing. So this material prints pretty well on those printers, and these are not terribly expensive. Let's see, what are their current prices for this? $1,000 on sale. Now, for some reason, it won't ship to some reason it won't ship to USA right now. Maybe you have to get a retailer or reseller to get these in the USA right now. I don't know. But these are pretty good printers for this kind of material. We can probably get our Ender 3 to print this, but not without some work. It's heated up. Let's try to resume our print and see if we can get anything happening. We're over here. Let's see. Nope, it's still, so instead of carrying on, because I don't think it's going to actually print with this, let's investigate what's going on here. Alright, so that's the kind of thing that you'll run into with some of these higher temperature materials. Now, things we could keep doing, just, I don't want to like continue on with that, but things we could keep doing if we didn't want to change stuff. One, we could drop the nozzle down a little bit to try and get it embedded in the surface a little bit more. Two, we could raise the bed temperature a little bit more. And we could possibly get this stuff to stick down. But then what you'll run into is this polycarbonate wants to separate. So we're going to have a lot of issues. So we've got a lot of little upgrades if we want to print materials like this. But before I do that, let's go over here and let's kind of walk through what's going on with these printers, and some of where we're going. So our next upgrade that I'm going to do on this printer is we are going to put the little spider hot end kit on here just so we can print hotter temperatures without having to worry about burning up the Teflon tube. But the other problem we had was over here, you know, we had some flow rate issues, and we could adjust our, request. So instead of trying to print as fast as we were, then we could just slow down the print and overcome the flow rate problems that way. But I don't want to do that. I don't want to slow it down just to get a better surface finish. I want to be able to print faster and still maintain a flow rate. So let's talk about flow rate for a little bit. So actually I'm in OneNote, but actually I want to go to MathCAD because I want to do some calculations. So the idea with flow rate, and maybe I do want to go back, there's a fly here. Maybe I do want to go back here. The idea with flow rate is that I have got filament. Let's just do red filament coming in here. So I've got filament, and then, it tapers down to whatever size nozzle I've got here. I've got to melt all that filament in, I don't know, somewhere in this region. So somewhere in there, I've got to melt all this filament to the point that it's viscous and it flows out the nozzle and I can lay it down where I want it to go. But that limits me on how fast I can push the new filament into that melt zone, because if I don't melt the core of the filament, then it's, you'll get some filament to come out, but it won't flow very well, and your surface finish won't be nice. It'll just not look very good if it works at all. So I need to melt all of that filament. So the idea is the heater block you know, it's emitting heat all into here. Actually in all directions, but I'm most concerned about getting the filament heated up. And that heater block, or the heater itself anyway, I know a couple of things about it. So on an Ender 3, the voltage for Ender 3 is 24 volts. That's just the way they operate. Most printers are either 24 volts or 12 volts. The Ender 3s are 24 volts. The heater cartridge. So here's a heater cartridge, like here. So this is what's inside the heat block. That's the little heater cartridge. It's really just a resistor. And so I can measure its resistance, and I have not done that on the one that's in the printer because it is inside the printer, so I can't actually, I could have to open it up and unconnect it to measure the resistance. But I know that it's a 40-watt heater, which is 14.4 ohms. Oh yeah, I don't remember where. Let's put ohms in there. There we go. So I know that. So if I know that the heater is 24 volts and the resistance is 14 ohms, then I can calculate the maximum amount of power that I can put in there. Power in is voltage squared over R. And if you don't know or remember these equations, that's fine. I will tell you what they are. And there's the 40-watt heater that I know I have. Now this heater, this is one thing you can also change if you want to print faster rates. This is a 60-watt heater. And it actually, trying to read it, I can't read. I think it says 60. I'm pretty sure it's a 60-watt heater because this one is like 10 ohms, 24 volts. That would be about 60 watts, 58, 59 watts or whatever. All right. So now what I've got to know is I've got to know a couple of things about the material. So C sub P, if you remember, or maybe you don't remember, or maybe you haven't taken that class yet, C sub P is heat capacity. And so for different materials, they have different heat capacities, meaning how much energy does it take to raise a certain mass of this PLA, for instance, a degree Celsius. So the heat capacity for PLA is 1.59 joules per gram Celsius. So what that would mean is that I have to put in 1.59 joules of energy, heat energy in this case, thermal energy, to raise a gram of PLA 1 degree Celsius. And so I can start to use that to figure out, well, you know, how much energy do I have to put in to raise all of this mass of PLA up to its melting point, right? Okay, so that's a piece of information. I also need the density. I'll need that in a minute. Whoops, that's not density. There's rho for density. Density of PLA. These are things that you wouldn't know. I had to look them up. It's not a number I know off the top of my head. So I looked it up, and density, all of these, I'm going to use PLA since that's what most of the time, most often gets printed. We can sub them out for polycarbonate or whatever if we want to. So 1.25 grams per degree Celsius, or no, not degree Celsius, centimeter cubed, sorry. That wouldn't make any sense as a density. So there's the density of whatever your material that you're melting is. We need a thing called the latent heat of fusion. So what this is material. We need our polymer, or PLA, to go from a solid, like the filament on the spool, into a, not a liquid like water, but a viscous material that's going to flow out onto our print surface. And the latent heat of fusion is a measure of how much heat energy you have to put in to make that transition happen. So for our PLA, this number, again, I had to look this up, 93.6 joules per gram. Okay, so that's just a thing that we have to look up. A lot of these are numbers that are material properties that you just have to find. Okay, so delta T, so delta T would be in the air around our printer. This is one of the comments was about a chamber, which we can change the air around our printer, and that will help not just with flow rate, but it'll help with other things like layer adhesion for certain materials and things like that. Right now, though, our printer is just sitting out in the open air, so the delta T is going to be equal to the temperature of our heat block, which we can set to, 215, or right now we had it at 240. We can set it to some number. Actually, let's make that a subscript. Minus the temperature of the air. So let's, it's going to give me a, it doesn't know what those numbers are, so let's put in some numbers. Let's say that the temperature of the block for PLA, kind of the hottest I ever print it is 215. Although 200 and 195 is fine. But let's say we're trying to figure out the maximum flow rate that we could achieve. So 215 is probably the upper end of how much you want to heat PLA. You can probably go a little higher. Let's say that the temperature of the air, depending on where you're at. So I'm out in a shop type area, so it's warmer. Let's just say it's 25 degrees Celsius. It's probably not. It's probably 23 or so, but let's just say 25. All of these we could go back and adjust and fine tune, but that's not really the point of what we're doing. Okay, so now there's this idea of heat flux. So heat going into a material. So heat flux for PLA, or for the PLA in our little melt zone here, is going to be the density of it. Oh, forget that it's not D, it's rho. Times the heat capacity, so how much heat does it take to heat up the material, times the delta T, so the difference in the heat block versus, we're assuming that the filament enters the hot end at ambient temperature. So whatever the temperature in the air around the printer is the temperature of the filament when it comes into the hot end. So this is probably not quite true, but it's close to true. Plus that latent heat of fusion idea. Those are weird units for what this is, pascals. Let's do joules per centimeter cube. So 500 joules per cubic centimeter of heat flux. Okay, how much that would tell us that based on how hot we're trying to print, the type of material we're trying to print, this would give us an idea that for every cubic centimeter of material we want to melt, we need 500 joules. Okay, so our power in, did I already do power in? No, I just talked about voltage and all that. Our power in is based on the heater. So assuming our power supply can provide all this power, then we had volts, because it was a 24 volt system. Oh, I did it right there. I did it right there. I thought I did. All right. So power in, we already decided that in this setup we have 40 watts of power going into our printer at most, into the hot end part. So now this Q is our volumetric flow rate. So we have two different Qs. That's fine. I'll call it flow rate, just so we know the difference. They're related to each other, but how much power are we putting in divided by how much power do we need per mass of material. I called this PLA since we were using these numbers for PLA, and let's just put it in a more normal unit here. So normally when we talk about flow rate of a printer, we do millimeters cubed per second. So if we went to Cura and looked at flow rate, those would be cubic millimeters per second. So 80 cubic millimeters per second. So that's the theoretical maximum, but we don't actually get that. We can't get even kind of close to that. So we get about, 15. Now, when we change out our nozzle, when we change to maybe a higher wattage heater, larger diameter nozzle, all metal hot end so we can print hotter, we can get closer, but getting to 80 is tough. But that's the theoretical limit. So there's something else that is keeping us from getting to 80. And something else is the amount of time that the filament stays in the melt zone. So all of this calculation doesn't take into account that I'm constantly putting new filament in because I'm trying to print a part, a three-dimensional part. I'm trying to lay down one layer and then add another layer on top of that. So I've got to continually supply new filament. None of that's taken into account here. So I need to take that into account, that I've got a limited amount of time to melt the filament. Only when it's in the heat block is it really melting. Anywhere else, it's not really melting. Maybe some in the nozzle and maybe a tiny bit in the heat break, but really just in the heat block is where it's melting. So let's take that into account. So you'll also notice, now that before we go do that calculation, let's look at a Volcano nozzle. So look at this nozzle compared to what you have on your printer. See, it's got a much longer set of threads. That's the whole idea here, is that these things have a longer melt zone. A lot of times, let's do Volcano nozzle hot end. Yeah, here we go. Let's look at this. So the heat block here is turned in a way that the heater, you can kind of see the edge of the bottom where there's that hole. That's where the heater goes. The heater cartridge is now going to be parallel to that long threaded nozzle, so that they're trying to get a longer melt zone so that they can get more filament melted at a time so that they can get higher flow rates. So, but we're limited. We don't have that. So we've got to figure out, in our limited melt zone, what can we possibly get. So we need to take a little different approach here. And let's see, do I want to, we would look at Fourier's law. Do I want to do that? We can write it down. So heat transfer rate, little q, is equal to our thermal conduct, or negative thermal conductivity. So that would be a kappa times the cross-sectional area of what we're trying to, or the area that we're trying to work across, times, dt over dx. So the what's that? What would that be? That would be the temperature gradient, kind of like what we did up here with the delta T thing. What we're going to do is we're going to use thermal diffusivity. So alpha. This is alpha. This is equal to, it's kind of like the ability of a material to conduct heat and to store heat. So a material with a higher thermal conductivity or diffusivity will melt faster. So it will be K, or kappa rather, not capital K. Or this is an approximation. I can't do approximation in MathCAD, so I can only do equals to, but this is an approximation. Over the density of the material times the heat capacity of the material, like that. So we have, well, actually we don't have K, do we? So that's another, or kappa. For PLA, if I can get it to type the letter I want. There we go. For PLA, this value, I had to look it up, 0.13 watts per meter Celsius. Weird units, but that's the way it works out. So our diffusivity is this little tiny number here. Now we've got the melt zone. So the melt zone here is I'm looking at what I did before, and I have two different diameters here, right? So all of this area has to come out of the nozzle. The nozzle diameter on my printer is now 0.08 millimeters. Nozzle diameter on most printers is 0.4. Let's use 0.4 just for a standard setup. We're going to need a new page. And all of this material has to come out of that nozzle size hole in the nozzle. So maybe we'll change this number to 0.8 to match our printer in a minute. So the time to melt all of this stuff and get it out the nozzle is equal to the cross-sectional area of the nozzle. So diameter of the nozzle squared, well, diameter, all right, I'm looking at my, I guess all of this radius squared over diffusivity, looking at the units. So radius would be this over, I may have to check that particular part of the calculations later, now that I think about it. I did these beforehand, obviously, to get all these numbers, the factors. But now I'm second guessing r squared there. But I think that's still right. All right. So based on now we have the material needs to stay in our melt zone for 0.6 seconds, something like that. Or well, see, I kind of wonder if this should be the diameter of the filament. Because most of the melt zone, if we look at I had it pulled up here somewhere. Here. So this is the cross section of a typical E3D V6 style nozzle, which most of these nozzles are. Most of the melt zone is actually 2 millimeters, or your 1.75 millimeter diameter. So all of it has to come out of the 0.4 or 0.8 in our case millimeter nozzle hole. But now I wonder if maybe we should do this. I'll have to think about that one some more, but we'll carry on for now. Let's do the side by side and see what happens. Yeah, that's way different. Okay, so what we probably actually need here, because what this is doing is, this is meter squared per second diffusivity, and now that I think about it, it probably needs to be the surface area of that cylinder of material, but we'll come back to that. Or maybe, yeah, it should be the surface area of that cylinder, I think. So we'll come back to that area. What would that be? Let's see. Area of the cylinder. Sorry, we're having to make it up as we go. This is a diameter of the filament. So we want the circumference times the length of our melt zone. So pi times diameter of the filament would be that times melt zone length. We'll just do L of melt zone. We'll do that. Which we don't know. So the length of the melt zone we could get from here. So the entire length of the nozzle is 12.5 millimeters. I'm going to say the melt zone is the part that's inside the block. So it's like 7.5 millimeters. Or no, 6.5, 7.5 millimeters. So let's do 7.5 millimeters. We could probably reduce that. We could tweak that number a little bit. Let's just do 7.5 for now. And let's change our time to melt to the area of the cylinder over that diffusivity. I'm not 100% sure on this part. Oh wait, did I not? I didn't get it in there. Diffusivity. Oh, put an extra period in there. Whoa, that's definitely not right. Alright, so let's go with what we had at the beginning. And I'll have to rethink through that. It's been a while since I did that thing. So I'll have to rethink through that. Let's go with that because that time makes sense. That it takes, you know, half a second or so of sitting in the melt zone for it to melt. So I'll have to think about that. But once we know how long it takes for our filament to melt to the core inside the melt zone, then I can figure out, well, how fast can I send filament through there in order for that to happen. So I could find a maximum feed rate would be equal to however long the melt zone is. So 7.5 millimeters is what I assumed, divided by the time it takes to melt. Did I not call it that? Oh, I erased it, didn't I? There we go. So there's our feed rate in meters per second. Let's do millimeters per second. 12 millimeters per second feed rate. So this would be the feed rate that our feeder that's sending the filament into the hot end. That's how fast we could send filament in. And then to figure out the maximum flow rate, we would set our, or we would calculate the area of our filament, which I don't have anymore. So I do have the diameter of the filament, and I have the d squared times pi. Wait, that's not how you do pi. Pi over 4. That's the area of the filament. So if I did Q at the max feed rate, so the volumetric flow rate set to the maximum feed rate is the limiting factor versus what we did before, where we got like 80 millimeters cubed per second, assuming that we could just melt as much filament as we wanted. But this one's limited to our maximum feed rate. A times, well, I called it F max, didn't I? And let's put it in millimeters cubed, because normally that's what we talk about. 30 millimeters cubed per second. And again, this is not considering that I've got any losses. This is a 100% efficient system. So it's thinking the very most maximum volumetric flow rate. This is a 0.4 millimeter diameter nozzle, is 30 millimeters per second, 30 millimeters cubed per second. Assuming that I can actually feed filament in this fast, which I should be able to, and assuming I did this part right, which I think I did, the time in the melt zone, I think I did that right now that I'm looking at it, but I do need to go back and really think about why I use the radius squared as the numerator for this time in the melt zone. Radius of the nozzle diameter, not the radius of the inside of the nozzle. But I guess that I'll have to think about that. And so it gives me a relatively high, you know, it would kind of make more sense if this was, so that would be pi times pi. Now it's the cross-sectional area. That makes a little more sense. I'll have to think about this one and see what area should I be using here. Should I be using the diameter of the nozzle, diameter of the filament, or some other diameter, or the surface area? It's an area, and I'm trying to think through how this is working. But this one gives me 9. I know I can get more than 9, but I couldn't get up to the 20 that I had before. Or the 30 I had before. But this also doesn't include that some of this heat is getting lost to the atmosphere. Some of the heat is not going into the filament, it's going into other places. So there are some inefficiencies that are not being calculated here. Mainly I wanted to walk through that so that you can kind of get an idea of why some of these different filament design, or not filament, but hot end designs exist. So like the Volcano, if you look close, was it this one? No, it's not that one. I saw it on one of these. This one. So if you look close at this one, where'd it go? That's not even. Oh, here it is. So inside there, I don't know if you can tell very well, but you see the 3 small. Oh, I can zoom in. You see the 3 small circles. What this nozzle does, and there are non-volcano style, so regular type of nozzles that we have for your Ender 3. What this one's doing is it has a divided chamber inside there, so it takes your filament, and as it goes into the melt zone, it splits it off into 3 smaller strands. So the idea being that 3 smaller strands are easier to melt to the core than one larger 1.75 millimeter strand of filament. So there are a lot of different ideas behind how you get filament melted faster, because that's usually your limiting factor on how fast you can print. Eventually you start getting mechanical limitations, like the printer vibrates too much and the surface finish isn't good. We will look at some different printers that have a different motion system from the Ender 3 that try to mitigate that. I saw in the chat there was this mention of Clipper. Clipper has some functions that also can even take an Ender 3 and help it print faster and not have those mechanical limitations, or at least mitigate them. It doesn't get rid of them, it just counteracts them. And so we'll actually add Clipper later on in the quarter also. But I kind of wanted to walk through, even if we don't have, even if we don't have this calculation quite right, there is some amount of time, minimum amount of time in the melt zone that is required. We might have to go rethink about what that should be calculated as, theoretically, but doesn't matter right now. The point is that there is some minimum. And then there are different ways. This one nozzle is trying 3 different things to deal with that. So 1, it is a longer melt zone. 2, it's dividing the filament into 3 smaller strands so that they can melt faster, creating more surface area to get the heat into the filament. And it's also got a different core material. So the part of the material where the metal actually, or not the metal transfers heat into the filament is a different material, particularly a different material that is better at heat conduction. So it looks like copper. I don't know if it's actually copper or if it says, it doesn't actually say on any of these. There's a better view of that 3 chambers inside there. Doesn't actually say what material is inside of there. These are from Temu, so, or Temu, however you say it. So probably wouldn't buy these particular ones. I'm just using them for their picture. But look at that. The melt zone on here looks like it's 16 millimeters. So it's, it's twice what we had in our other one. And if I take just that one change, and length of the melt zone is 16 millimeters all of a sudden, 16 millimeters though, then I'm up at double, well, because it's a proportion, so I'm double the flow rate that I can get. Whether I can get to 63, I don't know, but I can double what I was at just by being able to melt the filament, melt more of the filament at the same time. So those are some of the ideas. Let me see where we're at on time. I don't know. We probably would have time to change out our nozzle or hot end here. Why don't we instead open this guy up, see what's inside, and then next time we'll start out by actually mounting this here. So I haven't opened it yet, so let's see what we get. We saw the pictures of what we get, but I didn't actually open this one. Still can't open it. Okay, that, I guess it's gonna slide. Yeah, it slides out of there. So get the spider hot end. Let's get him on the picture here. So that's inside of this, and looks like we're supposed to peel that up. And a couple of tools. Again, we probably will use our own tools, and mounting hardware on there. And then here is the actual hot end. So it has its own special shaped silicone sock, so that's going to be hard to replace if we ever have to replace that. It looks like it's all tightly assembled. Sometimes with these hot ends that are pre-assembled, you want to take them apart and reassemble them. I actually think this is probably okay. We're going to assume it's okay, and see what happens. So what will happen if it's not okay is we'll get filament leaking out around that nozzle seat there, or possibly out the top up there. You can kind of see the heat break in there, and then there are two screws here that are holding the heat sink kind of stationary with the heat block. It doesn't have a thermistor or a heater in there, so we will have to use our existing thermistor and heater, or we could put in our 60-watt heater. I think maybe we'll do that since we've got we'll have more time to take everything apart anyway. I think maybe we will change out to a 60-watt heater just to get a little bit more. Go back to our calculations over here. Put them over here. We assumed a 40-watt heater. That is a 9.9 ohm, which is 60-ish watts. And oh yeah, let's go back to our no, we changed this, didn't we? Probably has a similar length melt zone. So we're still limited here, right? Because the limit on this is the melt zone, basically. So how much material, how long is the melt zone, which that looks pretty similar. Well, that looks pretty similar to the existing melt zone. So changing out the heater may not make anything. It'll make it heat up faster. So like the initial heat to 200 or whatever from room temperature will be faster. So we save a few seconds there. But in this situation, we may not gain a lot by here, since we're limited more on how fast we can melt the filament to begin with. This nozzle, it says it's 0.4, and it's one of the shiny ones. So typically what the shiny silver ones, they are usually a brass core with a nickel plating on the outside. So they're not hardened steel. They wouldn't do too well if we wanted to try our carbon fiber filled polycarbonate. They wouldn't do too well with that. But they're a little bit more abrasive resistance. Plus they're a little smoother. So maybe you get a little cleaner flow. But that's for next time. We only have like 5 minutes. I don't think we could tear this thing down and put this one in, change out all the heaters and everything in 5 minutes. So that's what we'll do next time. And I don't think that's going to help us with our polycarbonate printing. Won't really change anything that's going to affect that. We're going to have to do some other stuff to get to polycarbonate printing on an Ender 3. Just because they're really not set up for that kind of printing. But we want to see if that's, what do you have to do to get that to happen. And some of the suggestions in the chat, like a chamber, would help. Printing hotter. Now we can at least print hotter, so we can go up to 300. That could help with the flow a little bit. So will that be enough to get it to stick down to our bed? And maybe I can find some of this that's specific for polycarbonate. I might actually have some. So that's our next steps to printing some of these more exotic materials, or at least more difficult to print materials. They cost more, so I don't know if that counts as exotic or not, but they do cost more. All right, so we'll be back. Should be Wednesday, 9:30, and we're going to put this guy on, and we're going to see if that elevated temperature will help us print the polycarbonate and get it to stick to our bed. All right,